All right, today we're diving into one of the most fundamental tools in all of math, polynomials. Now, I want you to think of them like a construction set. We're going to start with the absolute basic building blocks and see how they snap together to create the blueprints that literally describe our world. I mean, have you ever looked at the perfect curve of a thrown ball, or the huge, graceful sweep of a bridge, or even the path of a satellite shooting through space and thought, how? How on earth do we predict that? How do you model something so complex with such precision? It feels like it should be magic, right? But nope, it's just some incredibly powerful math. And the answer to that big question, it lies right here. It's in these beautiful, elegant curves that are generated by these things called polynomials. They're basically the language we use to describe all those shapes. They let us turn all that complex, real-world motion and structure into something we can actually calculate and, build. Okay, so let's get into it. To really understand how polynomials work, we gotta break them down into their most basic parts first, the building blocks. So what is a polynomial anyway? Well, at its heart, it's just an expression made up of a few simple ingredients. You've got variables, letters like x, and you've got coefficients, which are just the numbers sitting in front of those variables. The really important rules are you can only use basic stuff like adding, subtracting, and multiplying. And, this is key, the exponents on the variables have to be non-negative whole numbers. So no fractions or negative numbers up there in the exponents. That's the main rule. All right, let's look at a real example to make this clear. If we've got this jumble of terms here, the very first thing you always want to do is put it in what's called standard form. That just means arranging the terms from the highest exponent all the way down to the lowest. Trust me, it makes everything so much easier to see what's going on. This table breaks it down perfectly. See, each little piece, like negative 8x to the fourth, we call that a term. The number out front, the negative 8, that's the coefficient. X is obviously our variable, but honestly, the most important piece of info here is the degree. The degree is just the highest exponent you can find in the whole thing. In this case, it's 4. And that one little number is the key, because it tells us a ton about the overall shape of the polynomial's graph later on. Okay, so now that we know all the parts, let's see how they actually fit together. This is the assembly phase, where we're going to learn how to add, subtract, and multiply these expressions. Adding polynomials is pretty easy, actually. You just find and combine the like terms. All the x squareds with the other x squareds, and so on. Subtraction, though, has this one little trap. You have to, and I mean have to, distribute that negative sign to every single term in the second polynomial before you do anything else. It is the #1 spot where people make mistakes, so always watch out for it. Okay, now multiplication. This is where things get really cool. If adding is like sorting similar blocks into piles, multiplication is like actually snapping them together to build something way bigger and more complex. A classic way to multiply two of these things, two binomials, is the FOIL method. It's just a handy little acronym to make sure you multiply every part of the first one by every part of the second one. You multiply the f first terms, then the outside terms, then the inside terms, and finally the last terms. Once you've got all 4 of those products, you just combine any like terms you have, and boom, you've built your new, bigger polynomial. So we've learned how to build these things up. Now it's time to learn how to take them apart. This is what I like to call the art of deconstruction, or as mathematicians call it, factoring. Yeah, it's totally the inverse process. Multiplication builds complexity, right? While division and factoring help us find those simple little pieces hidden inside all that complexity. It's kind of like being a detective for numbers. So, what is factoring? It's basically the challenge of looking at a polynomial, like that one we just made with FOIL, and trying to figure out what 2 smaller things did we multiply together to get this. It's all about working the puzzle in reverse. Let's check out this example. We start with the polynomial x squared minus 8x plus 12. So we do our detective work, our factoring, and we find its original building blocks were x minus 6 and x minus 2. Now here's the magic trick. If we set that original polynomial to equal 0, the solutions, which we call roots or zeros, are just the values of x that make each of those little factors equal 0. So in this case, what makes x minus 6 0? Positive 6. What makes x minus 2 0? Positive 2. They're your roots, 6 and 2. And this isn't just some neat party trick.
Factoring is the main way we solve polynomial equations. When you see an equation like this one set to 0, your brain should immediately think, okay, I need to factor this to find the roots. The roots here, 3, -2, 2, are the only 3 numbers in the entire universe that will make this equation true. That's pretty powerful.
All right, so we've done the algebra, we've found the roots. Now it's time to pull out the blueprint and see how all this work actually builds the graph of the polynomial. This is where it all becomes visual. So we have these numbers, our roots, but what do they actually mean? Are they just some abstract answers to an algebra problem, or do they tell us something real, something tangible about how the polynomial behaves? And here it is. This is the big payoff. The roots are called zeros for a reason. It's because they are the points where the function's value, its y value, is literally 0. So think about it. Where is a graph when its y value is 0? It's sitting right on the horizontal x-axis. The roots are the x-intercepts. That's what they are. The whole idea is this simple. Wherever that curvy line hits the flat horizontal line, you have found a root. These roots are like the anchor points for the entire graph. For any polynomial, if you know where all the roots are, it's like having the main pins on a map. It helps you sketch out the entire journey of that curve.
Okay, so why do we go through all of this? Because these aren't just, abstract exercises for a math class. These skills are essential, super practical tools, especially when you're up against something like the SAT. The SAT absolutely loves to test if you understand different kinds of growth. Linear growth, that's when you add the same amount each time, is a huge concept. And guess what a linear equation is? It's just a first-degree polynomial. It's a straight line. And that's fundamentally different from exponential growth, where you multiply by a percentage, which gives you that curve that just gets steeper and steeper and steeper. And a lot of the time, you'll see it boil down to this really familiar linear equation, y equals mx plus b. Don't let all the text on the screen distract you. That formula is the whole point. It is the simplest polynomial there is, and it's perfect for modeling things like a savings account, where you put in the same amount of money every month. Being able to spot when a word problem needs this linear model versus an exponential one is a major key to doing well on the test. So there you have it. We've gone from the tiny little building blocks of polynomials all the way to the blueprints they create for graphs, and even seen how they show up on major exams. You've basically learned the code. So the question is, now that you know the language, what patterns are you going to start seeing in the world around you?